Hey, okay, thank you guys. We're going to continue this FHE segment with Michael from Zama for our next talk before the break.
Right. Hello. Okay. Yeah. Thanks. Thanks also to Verifiable and Rick for a great introduction to my talk. Thank you. So this is based on joint work with Luis, who's also with Zama. And I want to talk about Verifiable FHE, which is something that we're very excited about, and I hope I can convince you or explain to you why. All right, since time is money, let's jump right in. What's FHE? Well, you just heard it, right? Like FHE is this amazing primitive that allows you to encrypt your data, send it off to a server, the server can compute on it, and send you back the result, and it never needs to decrypt. It doesn't need to know the secret key, it can just do it. And in this sense, it enables privacy-preserving outsourcing of computation. So you can, outsource your computation without having to compromise on privacy. And then you have this thing that you guys all know in the Snark community or in the zero knowledge community is this technology called Snarks, which is sort of complementary in the sense that it allows you to enable, or it enables verifiable outsourcing of computation, but doesn't have really privacy guarantees. Now, I'm ignoring the zero knowledge part of Snarks for this talk, which is, weird for a ZK summit, but bear with me. The kind of privacy you get from zero knowledge in this setting is a different kind, a different kind of privacy that what we want out for the input of the data of the computing party or of the client that's not doing the computation. So it allows you to do enables verifiable outsourcing of computation, but doesn't give you really the privacy guarantees that we're looking for. And so the natural question is, can we slap them together to get something what's called Verifiable FHE, which would allow you to outsource your computation both in a privacy-preserving manner and make it verifiable. And that's kind of like the dream of outsourcing computation, if you think about it, right? Like it's verifiable and private, which is essentially like running it on your own machine, is just you didn't have to run it on your own machine. It doesn't really get better than that. It only gets more efficient, hopefully. Let's see. But yeah, so that's what we're going to try to do. We're going to try to combine FHE and Snarks. I should probably say that there might be other ways to get this kind of primitive that allows you to do privacy-preserving and verifiable outsourcing computation, potentially. We're going to go the FHE and Snark route. And even if you look at the FHE and Snark route, you take a step back, there seem to be several ways of how you can maybe achieve this. There's two obvious ways you can do it. You can take your FHE scheme where you get a circuit that you want to evaluate on your plain text data. Your FHE scheme tells you how to turn that into a circuit on ciphertext. And then you can take this circuit on ciphertext and prove it using your Snark. So you can prove the ciphertext operations using the Snark. So in some sense, you're running FHE inside the Snark. You could also do it the other way around. You could potentially run the Snark inside FHE, which means, you have the circuit that you want to compute on your plain text, and the prover that proves that you did it correctly is also just a circuit. So you could also homomorphically run this inside FHE, right? And so you would homomorphically compute the proof inside the ciphertext. So these are two different, fundamentally different approaches of how to do it. And from a performance standpoint, it's not quite clear which one would give you the best performance. Probably depends on which kind of schemes you try to combine here. Interestingly, though, if you look at it from a security standpoint, there's a surprisingly clear-cut answer, which is you do want to run your FHE inside the Snark. You want to use the Snark to actually verify or prove that you did the ciphertext operations correctly. And why is this? That is because it allows the client to verify the proof first before it decrypts. And that is actually quite important. So from crypto, we kind of know that the decryption operation is a pretty sensitive operation because it involves the secret key and the secret message pops out. So as soon as there's any kind of signal that the adversary might get back from this decryption operation, it can try to tamper with ciphertext and try to learn something about the secret key or the message. And it really helps the security if you can verify first that nothing fishy has been going on with the ciphertext before you actually apply the decryption operation. Right? So I'm going to talk a little bit more about security later, hopefully, time permitting. But I just wanted to motivate what we're doing and why we're doing it the way we're trying to do it. Okay, I hope this is somewhat clear. You want to first verify and then decrypt. So what we're going to do is we're going to slap a Snark on the FHE instead of the other way around. Okay, So we have these two complementary technologies. We have FHEs, we have snarks. Are we done? Well, in theory, you could potentially say, yeah, but in practice, you run into quite a few problems when you try to do this. And the overarching problem here is that both technologies sort of incur an overhead, and the combination, gives you overhead squared, essentially. So with this in mind, we just talked about FHE, or Rick and Ravidal did. And in FHE, you have something that's called ciphertext expansion, which means if you encrypt your data, your ciphertexts are going to be larger than your data that you encrypted. So, but that also means that the ciphertext circuit is going to be larger than the plaintext circuit you were originally trying to compute. So the circuit gets significantly larger by encryption, because you're running it in FHE. Which, with snarks, we know that they're pretty sensitive to the size of the circuit. The larger your circuit, the slower the prover, and also the more memory-intense the prover. Second, you just heard, you have this bootstrapping operation, which in any FHE scheme, like all FHE schemes that we know of today, need to do this because they all work with noise. So at some point, you will have to do it. And it is typically the costliest operation in your scheme, basically always. And to the degree that it's basically infeasible for large circuits, for snarks to prove, as we'll see later. And then in FHE, you typically have your operations. Your ciphertext operations are usually native operations over rings. Very common is this ring ZQX mod x to the n+1. It's just one example, but that's just to give you an idea of what kind of rings we're talking about. And even this ZQ in front, the Q is typically not a prime. In TFHE, it's usually chosen to be 2 to the 64 or something to make operations very efficient. Other schemes need this to be like a product of many primes, and so there's different requirements for different schemes. And typically this is not a prime, so you can't really usually rely on prime fields, while most snarks do have their operations natively over finite fields, and that's important for security. So there's a mismatch here to some degree, and also in FHE, especially this bootstrapping operation usually requires some non-arithmetic operations, as Ravital and Rick pointed out. Like many schemes are good at doing multiplications and additions, but the bootstrapping really often requires like non-arithmetic operations, and then this is not always very well supported in different snarks. Again, with all of these, the issue is usually more nuanced than what I'm saying here. I'm trying to stay on a reasonably high level. But this is sort of the general picture, the general problems that you run into when you try to combine these things. Okay, so what do? Well, we try the best we can. We try it anyway. And the first thing that we're going to do is we're going to pick a very, very lightweight FHE scheme. And with that, I mean TFHE, not just because I'm with Zama, and at Zama we do like TFHE. There's good reasons to pick TFHE for this kind of combination. Because it has it's relatively lightweight. It's a third-generation scheme that uses a very, very light bootstrapping, right? Like it was explained before. You have this Gen 2 and Gen 3 kind of FHE schemes, and the Gen 2 schemes you can think of maybe like as I like to think of them as like these huge trucks where you can put a bunch of stuff in, and then get it from A to B. It's going to take you a while, but you can transport a lot of stuff at the same time. So your latency is going to be not great, but your throughput is going to be pretty reasonable. On the other hand, these third-generation schemes are more like little sports cars, right? Like all it's going to fit is like your shopping bag, but you're going to get from A to B really, really fast. And so, latency is going to be good. Throughput, depends on how many sports cars you can drive, I guess. So, and when you're going to try to apply a snark to something where it's going to be challenging anyway, maybe not try with a truck, maybe try with a sports car. So that's what we're going to do. And this has also, like TFHE, has this nice feature that it can be parameterized with different ciphertext modulus. It's like the ciphertext modulus is structure that doesn't really matter too much. As I said, usually it's selected to be a power of 2 for efficiency reasons, but it doesn't have to be. Actually, the scheme works just like picking any modulus. And so, looking ahead, as you can see, what we can do is we can make it a prime, and we can pretty much make it any prime we want, as long as it's sort of like reasonable within like sort of this roughly the same size as what we usually use for TFHE. Okay, so we're going to match TFHE up with Plonky 2. So Plonky 2 I'm assuming it's you're familiar. Most of you are familiar with it. It's a great snark. It's like it's a combination of Plonk with Fry, and it's concretely very efficient. There's like very efficient implementations out there. It's a snark that is transparent and publicly verifiable, which are nice properties that's going to carry over to our VFHE scheme when we do this combination. And it, very nice feature is also that it works with small fields. It works with this prime, which is called the Goldilocks prime, which is around 2 to the 64, right? Like a 64-bit prime, which makes for very nice efficiency, but also it sort of matches sort of the parameters that we typically choose for TFHE to make this efficient. So it seems these two things just seem to match up quite nicely. All right, so are we done? And when we do this, do we get a nice scheme out? Well, as it was maybe explained before in TFHE, there's two operations we need to support, which is one is addition, and the other one is a programmable bootstrapping. Now, addition is pretty easy. Like addition is literally just like adding the ciphertext vectors. So your ciphertext expansion is going to take your data, turn it into a vector, and the addition of the two values is like literally just adding these two vectors. So this is pretty straightforward also to do in a snark. But what about the bootstrapping? Is that efficient? And unfortunately, the answer is no. We tried this. We tried to throw Plonky2 just at, we designed a circuit for this bootstrapping, tried to throw Plonky2 at it, and we even very large Amazon instances with huge amount of memory, with 512 gigabytes of memory or something. They ran out of memory just trying to do this, even for moderate parameters. Not even real parameters, just even smallish toy parameters. It didn't work. So we have to do something more clever here. And so this is where we are going to take a look at the structure of TFHE's bootstrapping. And I don't want you to try to fully understand how the bootstrapping works just from the slide. This is a schematic view of TFHE's bootstrapping. What I want you to notice is that it's essentially a long loop. The core of the TFHE's bootstrapping is what's called the blind rotation, and the blind rotation is essentially a loop that goes from 0 to n. And this n you can think of roughly somewhere between 500 and 1,000, depending on the parameters. That is the core of the programmable bootstrapping of TFHE. Right, and now you might wonder, well, we do have techniques for this to solve this, right? Or to prove this more efficiently than just unrolling the loop in a circuit. And you're right, yes. We can employ IVC to actually do this proof here. And there's a couple of ways to construct IVC. This term has been flying around here for a while, all day. And the more modern approach would be probably folding. But Plonky2 is not really set up to support folding. So we're going to do the classic route of doing recursion-based IVC. So the basic idea of recursion-based IVC, if you don't know, so the idea is that in every loop iteration, you're going to prove that your loop iteration is correct. But you're also going to prove that all the previous loop iterations were correct by verifying the proof of the previous loop iteration. It takes a moment to wrap your head around if you don't know, if you haven't seen it before. So what we're going to do is every loop iteration is going to be complemented with the verifier circuit. And the nice thing about Plonky2 is that it's optimized for recursion. So it's very efficient at proving its own verifier circuit. And so this makes this kind of implementation actually quite efficient. And with this kind of technique, we were actually able to improve the bootstrapping actually fairly easily, even on consumer laptops. So you'll see next. So there's a lot of technical details that I'm slipping under the rug here. There's a paper that I'm going to link to at the end of at the talk. Go look at it if you're interested. But so I want to just present the results real quick. These are the parameters that we ran, that we experimented with. And these are pretty typical parameters that are secure. So you can use this for correctness and security. It's going to work. Q, as I said, is a Goldilocks prime, which matches the Plonky2 finite field that it's working over. The n, the small n, is the parameter that determines how long the blind rotation is, the number of steps in the loop. The capital N is sort of roughly corresponds to your ciphertext expansion. K, B, and L are parameters, and the base beta before in the talk before is is this capital B here, sort of, and L, these are decomposition parameters that impact the size of your circuit, but I don't want to go into detail here for now. But yeah, so these are typical parameters, I would say, for TFHE, and these are the results that we got, and we really focused on trying to get the prover time down and using manageable memory. And what we got was prover time that's in the range of like 20 minutes for large AWS instances. So 20 minutes for a single bootstrapping operation is fairly slow. I realize that. But the main takeaway is here, it's not ridiculous. It's not absurd. Like, you can run it. It's great. So for most applications, this is going to be too slow. But things usually always get better, or more performant at least. So the hope is that with better techniques, maybe snarks that are better tailored to FHE, or even FHE schemes that are better tailored to snarks, we can get this down a fair bit. All right. So now I've talked sort of about doing this in practice. What can this give us? And then we looked at this and was like, took a step back and we're like, okay, what does this actually give us, like in terms of security? Like, can we prove that this gives us nice security properties? And this is where the academic and me sort of like took over and really wanted to get to the bottom of this. And so, I forgot to mention, sorry. You can play with the code. It's online. It's also in the paper. So, but please do not use this for anything that's worth anything. Like, this is really just like academic style code that is not meant for production at all. All right. So let's say, okay. So I wanted to talk a little bit about security, and what we can prove actually about this combination of using an FHE and a snark. Can we actually prove that this gives us anything like in terms of privacy and verifiability? Like, is this combination actually sound? Like, does it give us anything? And the answer is yes, we can actually prove something in a fairly strong model, but we do have some key requirements for the protocol and how this is deployed. Right? Like, one is, as I mentioned before, it's important that you verify first and decrypt second. Like, whoever is in your protocol, whoever is decrypting, should also always be verifying first. The second is that the client who's decrypting, or actually not decrypting, the client that is verifying, actually needs to know the circuit and the input ciphertext. Like, they need this for the verification. Like, you could imagine like doing a snark where you where these are sort of like witnesses of the server, and then the client could potentially use an extractor to gain them. But in that sense, our proof breaks down. So for our proof to work, you really need the client to know the circuit and the ciphertext that the snark was actually using, or the server was using to compute the output ciphertext. And you need to be sure that the input ciphertext are well formed. Otherwise, the server could play with the input ciphertext, or somebody else could play with the input ciphertext. And which would also allow it to play with output ciphertext just by extension. And so it could play with the ciphertext and still prove that it did things correctly. So these three things are sort of key requirements we need for a proof to go through. But if you do have and we do design like a very simple protocol, like a super simple protocol for outsourcing of computation, which is kind of the simplest you can think of, but it has some, what does this laptop do, or like what does a client do when the server behaves in this way, etc. You need to, some things that you need to take care of, but essentially it's the simplest protocol that you can think of. And we can actually prove security of this protocol in the UC model, which is, UC stands for universal composability. It's a very strong security model. And what's nice about this is that you can even reveal decryptions to the adversary. Even if you're in an application where the client sends off data, retrieves the data, retrieves the output ciphertext, decrypts it, and says, "Oh, this is cool. I want to publish this," publishes this, then for this protocol in this protocol, you can guarantee that the server actually doesn't learn anything beyond the ciphertext. Well, obviously it's going to learn the ciphertext, but it doesn't learn anything about the key or anything else. And that's a big no-no for FHE if it's deployed sort of like without a snark, for example. Then you have to be careful about these kind of things. And so this is like in crypto terms, what I'm saying here is that in this setting, you're even secure against a fully malicious adversary, like against an adversary that is actively secure, while usually FHE is only passively secure. Okay, so this sort of strengthens the security of your FHE scheme, but again, very important, this first condition for this to hold. Okay, and now a little bit of applications, what we think, what we have in mind, or what we can use this for. Well, I said, TFHE supports 2 operations, which is additions and bootstrapping. Right now, we can only do one bootstrapping, like prove one bootstrapping, but we can, adding additions before it is relatively easy. Like we can do this now with our prototype implementation, and then we can already support functions of this form. Again, it takes 20 minutes, it's slow, but we can do it. And if you look at this kind of function, well, if you think of F as sort of like as like an activation function, well, you got a neuron. You got a neuron in like a neural net. So, it doesn't take too much imagination to see that maybe at some point we'll be able to actually prove neural nets, and which would enable like verifiable and private AI, which would be very cool, I think. And then there are applications in blockchains with private transactions where you run your you run FHE in the blockchain, and here there's potential to like reduce the number of validators to 1, which might not be actually saving on this computation, on these computational resources might not be the killer here. What would be really cool is that you can reduce the trust in the, like, usually if you run this in this kind of blockchain, you need to trust the majority of validators, or you need to trust that the majority of validators is honest and doesn't collude. You could remove this assumption essentially. And then also you could envision like rolling this out in this sort of like hybrid rollups that in these private transactions, where the proving time might not actually be that much of a problem, right? Like in hybrid rollups, you only like actually need to provide a proof in case there's a dispute, and in that case, that hopefully happens very rarely. And if then the proof takes maybe a few hours, you might be okay here. So there might be applications that are sort of like within reach. I said like 20 minutes for one bootstrap. You would want multiple bootstrap, many bootstraps, but we might not be that far out from actually applications as this might seem at first. And this is sort of like what I want you to take away. If you have any more questions, I'm here, obviously. To talk to me after this or ask questions now. And also, this will take you to this paper. This and this are the same thing. Yes, and I'm open for questions. Thank you.
Thank you very much, Michael. So we have a question here. I don't know who was first.
Hi, thank you for the talk. So you were mentioning that TFHE is kind of a third generation schema in FHE, but I see here that you kind of combined it with Plonky 2, which is superseded by Plonky 3, and there's like other new proof systems. So did you consider combining it with kind of the newer systems for ZKP?
Yep, yeah, so since you mentioned concretely, I think Plonky 3 is not actually a snark itself, it's a toolkit to build snarks, and we haven't, like, you could potentially use it to build a snark that is more tailored towards FHE, for example. That is a research direction that we haven't looked into yet, but is definitely something that is promising. And we have looked into other schemes. A lot of them, though, so a lot of flurry has been happening in the realm of folding, and that would be very interesting to look into. But a lot of, like, so far, a lot of folding schemes rely on like discrete log-based systems, which have some algebraic properties which are nice, but they also need like very large fields. And in TFHE, we like to work with small fields, like 64-bit.
1 bit is good enough?
Sorry?
How about 1 bit or 8?
What do you mean?
1-bit fields and 8-bit fields. Like
yeah, you
Binius
could.
does that.
Who does that?
Binius.
Okay.
Okay. Yeah, we'll talk later.
Talk to me afterwards, and
Sure.
we can take this offline. Yeah, sure.
Nice shill, nice shill. The other side. Yeah, we have another question here.
So I have 2 questions, but I don't know if I have time. So
Go for it. Go for it.
So the first one is you mentioned that you needed IPC, which I understand. But I wonder, you didn't go with PCD for any kind of reason? Because with IBC you need to fold sequentially if you were to do it. But with PCD you can fold in parallel, like as if you had a tree, and therefore you get logarithmic increase of speed up. So is there any reason why you decided to go IBC only or brute force recursion with Plonky 2, aside from the fact that Goldilocks is of course a field that matches well the FHE primitives?
So the question was why we're not using PCD, why we're using IVC instead of PCD. So, I mean, we were focused on this one bootstrapping, and bootstrapping is really just a loop. So, you know, for that, IVC is like, as far as I understand, PCD is sort of the generalization to like larger computation graphs, right? Which is not something we need necessarily for the bootstrapping. So.
So you have performed your bootstrapping already, right? So you have all of the intermediate results of the computation. So that means you can fold in parallel absolutely everything that you have. Like you don't need to go sequentially one by one. You can just start building a Merkle tree and go to the top. So you go logarithmically faster. Yeah.
Okay, so it's a question.
So this is the difference between the PCD compiler and an IBC compiler within these kind of schemes. So I was just wondering why going IBC if you can go PCD, which can like deliver much better asymptotics.
Right. And why not? Why instead of doing the loop, why not do it in a tree? And yeah, like why do we do it sequentially and not like in a tree?
I understand why it's done like this, because bootstrapping it's like this. It's like FFTs at the end or entities or whatever. But like, why, when you are building a circuit or verifying this computation, you don't go towards this route of PCD, which would be like likely better?
I think the PCD would be very natural for the next step, which is proving multiple bootstrappings like in a circuit, and then sort of like combining this into like this is where I see the natural application of PCD. You could also potentially apply it to the bootstrapping and see if you can get a faster prover out. Sure, this is sort of like our first try how to do it, and I think there's like much to improve here, and I would invite everyone in this room to try to get your hands dirty and try to make this better. That would be great.
The other thing is there's one paper, I don't recall the name, which basically tries to amortize all of the bootstrapping that you need to perform within a single one, but the constants are terribly bad. Do you think that some kind of scheme like this, which you don't really care that much about the constants because what you want to do is prove the computation rather than actually executing it by itself, do you think that these kind of schemes could make some sense within what you're trying to do?
It could. I think I know the papers that you're talking about, and I haven't really thought about it too much yet, but it could work. Yeah, it could.
Thank you.
Yeah, thanks.
Do you have opinion about lattice-based proof systems, like lattice fault? Would they solve any of the non-native arithmetic or non-arithmetic operations constraints?
Yeah, potentially yes. We haven't. So for lattice-based snarks, there's not that many like very efficient implementations out there. Like one thing about Plonky 2 is that like it's very efficient and it's just out there and you can just use it. With lattice-based snarks, I think they could be useful. Lattice fold, we'll see. Is also something that's sort of on our agenda to explore. But one thing is that so folding schemes seem to be or their promise to more efficiency is that you don't have to prove the verifier at every step, right? Like you fold these things together, and so folding is usually simpler than doing the verifier circuit. In our case, actually, one step of the loop iteration of the blind rotation is already a pretty big circuit. We're talking like 2 to the 20 something, right? And like gates. And the verifier circuit, though, is much, much smaller for Plonky 2. So I'm not sure if folding really gives you that, like we'll see, but, we hope to see. We hope to get some better results, but it's unclear how much we'll get from this.
Yeah, I guess the more interest about is the lattice part of that, specifically to avoid some of those complicated parts with lattice-based FHE.
Yeah. So the hope would be, for example, that you could prove efficiently TFHE with the power of 2 modulus, for example. That could be very cool. Yeah.
I think PSC team, Privacy and Scalar Exploration, are working on the lattice work, which is like a framework for building lattice-based systems. So it might be interesting to explore that.
Okay. Thank you.
Yes.
Okay, we'll take the last one.
Hey, Michael. Thanks for the talk. I had a question on alternative approaches. So on one hand, you could basically code the bootstrapping in Rust, run it through RISC-0. On the other hand, you could just run the bootstrapping through a TEE.
Right.
Have you compared either approaches, and where does your 20 minutes proving time fall in between those two?
So, we have a comparison essentially with the ZKVM approach. Unfortunately, ZKVMs introduce a lot of overhead, and for the kind of circuit that we were trying to prove, they're much slower. And also, to the extent that we weren't actually able to run the entire thing for practical parameters. We didn't look too much into it. With some tweaking, maybe it would have worked. But from micro benchmarks, it seems like we are at least 2 to 3 orders of magnitude faster with the Plonky 2 circuit.
Great.
With T's are probably going to be much faster. But from a trust standpoint, or from security standpoint, you're essentially just shifting the trust to somebody else, right? T's are cool, but you're just instead of having to trust the person who's running it, you have to trust the person who gave them the hardware. So I mean, yeah, in certain applications, useful, but not the same as running it on your own machine, right?
Yeah,
it's not as cool.
It's not a fair comparison.
Yeah. It's not a fair comparison.
Yeah. Thanks.
Yeah.
Thank you very much. So we're going to have a break now, half an hour, and we'll be back for lightning talks at 3:30. Thank you very much, and thank you, Michael.